Turn on a tap and fill a glass with water. Clear, colorless, looks harmless. But that simple glass tells a long chemical story, because not all water is the same. Let's go a little deeper. Water chemistry focuses on what's dissolved in water: minerals, salts, gases, and sometimes harmful substances. These tiny differences decide whether water is safe to drink, good for cleaning, or damaging to pipes. Here's something even more interesting. Some water is called hard water. It contains dissolved calcium and magnesium ions. Hard water doesn't harm your health, but it leaves white deposits on kettles, blocks pipes, and makes soap less effective. That's why soap doesn't lather well in some places. But wait, here's the twist. Hardness isn't permanent. Water can be treated using simple chemical processes, boiling, ion exchange, or adding specific compounds to remove hardness and improve usability. Now let's go even deeper. Natural water isn't automatically safe to drink. It may contain bacteria, suspended particles, or dissolved chemicals. That's why water purification is essential. Filtration removes solid particles. Disinfection kills microorganisms. Chemical treatment adjusts pH and removes harmful ions. Only after these steps does water become potable, safe for human consumption. Let's connect this to real life. Drinking water systems, swimming pools, industrial cooling systems, agriculture, all of them depend on controlling water chemistry precisely. Before we wrap up, zoom out for a moment. Water may look simple, but chemically, it's one of the most carefully managed substances on Earth. Clean water isn't luck, it's chemistry working quietly in the background. And that leads to the next question. If metals interact with water and air, how do their unique properties make them useful in reactions, colors, and catalysis? That's exactly where we go next.